Hello again. Today we'll be talking about PCA for visualization and data exploration. Recall the wines dataset, which contained 178 wine varieties and 13 features measured on them via chemical analysis. In this dataset, if we selected random features to visualize the data by, it could be random pairs or perhaps triples of features, the visualization would feature a lot of points clumped together. This may not reveal groupings in the data that are important. For example, these labeled cultivar groupings of the data are highly overlapping. Moreover, they may not reveal the full spread or heterogeneity in the data. In short, the data is not organized well by random features. This motivates us to use a principled method like PCA. When you visualize the data with PCA, you're actually visualizing the first two PC components. Recall that sigma is the data covariance matrix, and the eigendecomposition of sigma yields eigenvectors u and eigenvalues lambda. The principal axes, or the directions that PCA uses, are in u, and these are the eigenvectors of sigma. The principal components of the data are x tilde, which is equal to u times x. And then visualizing the data involves drawing a scatter plot with PC1, or the first principal component, on the x-axis, and PC2, the second principal component, on the y-axis. This is a PCA plot of the wines dataset. Here we see that the three labeled cultivars are actually very well separated. Moreover, we see a high degree of separation between groupings in the data in a way that maximizes the spread of the data. Furthermore, PCA has the advantage that we can interpret these axes. We can look at how the original features are loaded onto these axes. These bar plots here show the loadings of the first principal component and the second principal component. We see, for example, that alcohol has a negative loading on PC1 and a positive loading on PC2. We also see that something like ash does not have much of a loading on PC1. When we actually color the data with these features, we see how these individual features are contributing to the principal axes. So malic acid, for example, is highly separating both PC1 and PC2, alcohol as well, whereas ash is sort of randomly scattered throughout this space. This means that we can actually characterize the groupings that arise by ways of the original features. What about the other PCs? The other PCs too can explain important variance, as is revealed in this Scree plot. In this Scree plot, we have the explained variance, which is actually equal to the corresponding eigenvalue for each of the eigenvectors. Here we see that there are about 3 significant eigenvectors. This means that we could also visualize this data with PC2 versus PC3, and that this actually provides really good separation and identification of cultivar 1.